Welcome back. Our previous video introduced how to estimate the parameters of a very simple and contrived unidimensional learning model. And hopefully this was illuminating to you about how to actually interpret the results of these models and how to take them to data. And today I wanted to do something similar, but for the multidimensional learning case. And what's interesting about this case is that even if I only receive one signal, I can update my beliefs about all of the different parts of my ability vector to the extent that there is correlation among the abilities or whatever I'm learning about. And as in the previous video, we will come up with an overly contrived example to make estimation easier. But then at the very end, we'll talk about how to make this more realistic and what would be involved for that. So we're going to estimate a multidimensional learning model. And the easiest analog to this would be learning about skills or productivities in different occupations. And that also ties in nicely to the wage residuals from the previous video with the unidimensional example. So now we pretend that we're in a situation where we can choose from 6 different occupations, and our productivity or our ability to perform the work in these different occupations is correlated with covariance matrix capital delta. And so my ability vector is going to be distributed multivariate normal in the population, mean 0, covariance delta. And while this may not be required in practice, in this particular setting, it does not really make sense to allow for multiple signals to be received. In truth, I could be working 2 part-time jobs in 2 different occupations, but we're just going to assume that away for simplicity. So I only get one signal in whichever occupation I was working in that period. And then the idea is that information in that population covariance matrix is going to allow me to update my ability belief in all the different occupations, even if I'm only participating in one occupation at a time. And I'm going to have a very similar wage regression as before. Now I have J subscripts as well to emphasize occupation J. And what are we hoping to get out of this? Well, first we're going to assume that the occupations are assigned randomly. I realize this is a silly assumption, but it's what we need to do to make this as simple as possible, and it's much better to start simply. Then we place distributional assumptions on the ability vector A and the noise epsilon, and A is bolded here to emphasize that it's a j-dimensional vector. Epsilon is also bolded. You may not be able to see it, but that's also a j-dimensional vector. And then we want to estimate the parameters by maximum likelihood, just like we did in the past video. It's just the case that now capital delta is a 6x6 covariance matrix, and sigma squared epsilon, which is now bolded, is a 6-dimensional vector. And then once we have those parameter estimates, we can use them to back out what each person's beliefs are at each point in time. And then we can also show that observing a signal in one occupation can be informative to others that I haven't yet chosen or been assigned to work in. And then another nice thing, because of how we've contrived this example, there's no occupational choice, and because of that, we can just do equation by equation OLS to estimate these learning parameters. And then we get our estimate of the variance covariance matrix by looking at the average within person residuals and then compute the correlation or the covariance of those across all people in the sample of data that we have. So what would this look like if we had to actually handle the endogeneity of occupational choice? Well, this would get us to a situation where the signal that we receive is a function of the belief in the ability, because people would probably want to work in occupations that are with their comparative advantage. And so what we would have to do is introduce a choice model, an occupational choice model, along with our wage model. And we would have to include some sort of permanent unobserved type to be realistic about sorting on different types of unobservables. So in particular, we could put an unobserved type dummy indexing type R in the X matrix. So now I've added an R subscript to the XIT. And then we allow the decision of which occupation to work in to be a function of the belief in each of the abilities. And that would give us a cohesive model where these ability beliefs could reinforce the downstream occupational choices. How would we estimate a type of model like that? Well, basically, we would have a nested EM algorithm. So why is it a nested EM algorithm? Well, the regular EM algorithm would handle the unobserved type R and allowing us to treat it as if it was observed. And then we could have another EM algorithm to handle the fact that we don't observe the abilities in the wage equation. And so there are econometric papers that have been published that show how to do this, and we'll briefly touch on them in the video that follows this. But basically, my outer EM will allow me to get the unobserved type probabilities in the population, the posterior unobserved type weights that I use in all the estimation processes, as well as the parameters of the choice equation. And then my inner EM algorithm, I take those unobserved type weights as given from the outer EM, and then I use my inner EM to get the beliefs about the abilities and estimate the parameters of the wage equation, since that's what's forming our learning signals. So that is how that would work. Let's go back to the tractable case and go through some code and see how we could use this in a real life example. So let's go back into Julia and look at some code. And in this code, because our example is very particular and contrived, I've generated my own data that fits the bill for what we want to accomplish. We don't have any specialty packages that we need to read in. I have a function that's generating the data. We're drawing abilities from the multivariate normal, that's 0 and covariance delta, and then we're drawing the other components of the wage as we were before. So I have 10,000 people, I have 20 periods per person, and I have 6 occupations to choose from. And then I'm choosing values for each of these parameters. We could estimate different versions of the model where we restrict these parameters to be the same across occupations, but given that we're just doing equation by equation OLS to actually get the estimates, this is going to be fine. And then I wanted to walk through what this 6x6 covariance matrix looks like. And I wanted to set it up so that the first 3 occupations are highly correlated with each other, and the last 3 occupations are highly correlated with each other, but there's not as much off-diagonal correlation among these groups. So this covariance matrix is close to being block diagonal, and this makes sense if you think that some subset of occupations uses more manual skills and other set of occupations uses more cognitive or executive function parts of the brain. So that's just kind of the underlying reason for why I set things up that way. And then we have these idiosyncratic variances that are part of the signal as well. So we simulate the data, and then we can just do equation by equation OLS. So basically I'm looping over occupations, just grabbing the rows of data that correspond to that occupation. And again, back in the original data generation, we just assigned occupations randomly right here. So I've got my OLS estimation, and then I'm getting the residuals, and then I'm computing the average residual per person and occupation, and the within person variance per person and occupation. And then once we have that, we can just get the correlation in those quantities. That gives us an estimate of the delta and the sigma. So the idiosyncratic variance is just going to be the variance in the residuals averaged within person, averaged across people. And then the covariance matrix for the abilities is going to be the average residual, correlate those across people. And this would change if we had a more realistic model, so I don't want to spend too much time breaking that down. But the point is we can estimate these parameters, and then once we have the parameter estimates, we can go through the belief updating formulas that we had from a couple videos ago. And so for each person, we can see how would their belief get updated if they received this signal and the learning system parameters were like so. And so every person in every period is going to have a vector of prior means and an individual covariance matrix of what they believe their ability to be in terms of the variance. So hopefully you'll see some of this here where I've got the inverse of the inverted variance plus omega, and I've got the variance times the inverted variance times the prior plus the omega times the signal. So these are exactly the formulas we had on those slides a couple videos ago. And I didn't go through to actually store the posterior variance, but that's what that's doing. And then I'm printing out how the beliefs get updated for one person in the data. So that is how that works, and then we can run this in our Julia terminal. That's finished now, so let's pull up the results. So I generated the data, and we've got very close results for all of the OLS estimates. And then for our estimates of the idiosyncratic variance, we got very similar estimates for those. And then for the variance covariance matrix, I apparently did not print those out, but those are good from what I recall. So let's go back and change the code and do that. Okay, so I went through and fixed the code and printed out the correlation matrix, and we can compare the estimates with the true values. So a lot of these numbers are very similar, and so it looks like we got a reasonable estimate of these correlation matrix parameters. So now that we have those, we can look at what are the beliefs of this person. So in the first period, person 1 was assigned to occupation 5, so they got a particular signal from occupation 5, and then they updated that according to the population covariance matrix, which was their prior variance at the start of the history. And you'll notice that they updated these other 3 abilities that were all highly correlated in proportion to the signal, and then they updated the other abilities as well, but not by as much because they're much more weakly correlated. So we can see that the degree to which the signal informs the posterior belief is in proportion to the level of correlation among those different abilities. The other thing I wanted to point out is that all of the elements of the correlation matrix are positive. So there's no negative correlation in these abilities, and so that's why all of these are becoming negative, is because the signal was originally negative. And then in the next period, they get another negative signal, so they're going to update the posterior even further, and everything's staying negative. And then in the next period, they're getting a negative signal again, so they just happen to be assigned to occupation 5 in each of the first 3 periods, and they got a negative signal in all 3. So their posterior is staying negative. And then they get a pretty strong positive signal in occupation 2, which is going to flip the sign of their posterior belief there, but it's not going to affect the belief in this other sector as well. And so then they get another negative signal in choice 5, and so then that's just sort of solidifying what they already knew. And again, I'm not showing the posterior variance matrix, but this posterior variance covariance matrix should be tending towards 0 as more of these signals are being received. All right, so that is how we would estimate a correlated learning model. And obviously I gave you the most contrived and simple setting in which to do that, but hopefully it was still informative to you about how these models operate. And then if we wanted to make things more realistic, it would actually induce quite a bit of complication, and so I didn't want to touch on that in these videos. But in the next video, I will cover some papers that are classic in terms of their treatment of the learning problem, as well as some papers that are econometrically impressive in terms of applying frontier methods like this nested algorithm that I referred to. So I hope that you found these videos on learning interesting and entertaining and informative, and that you'll stick around for this last video and see how these methods are applied in different subfields of economics today.